Right, this is the fourth and final part of the Paper 2 warm-up video 2016. So we got, in the last one we got almost to the end of the identification question. So let's get started. I'm going to scroll through now very quickly. Very quickly indeed. So, but I've scrolled through to the wrong place. Much better. Okay. So we're just finishing off the identification question, and the question asks us what is seen when you add silver nitrate solution to lithium iodide. And you should know this is the test for halides, and if you have a look on the right hand side of your periodic table, halides are in group 7, so we've got chloride, bromide and iodide. And chloride forms white precipitates, bromides form cream precipitates with silver nitrate, and iodide, where it gets slightly darker in colour again, it forms a yellow precipitate. So you can see that as you go down the group, the colour of the precipitates gets increasingly yellow. Chloride white, bromide cream, iodide yellow. And it asks us here for a chemical equation, which means either, well, it means a symbol equation, and you guess that from 3 marks. It also tells us to include state symbols. So we've got silver nitrate and lithium iodide. Now it tells us we've got a solution of lithium iodide, so that's aqueous. And the identity of this yellow precipitate is that it's silver iodide. So the silver ions and the iodide ions come together to form this precipitate, and that's a solid because it's a precipitate, and the ions left over are lithium nitrate, which is in solution. You might think, could I draw an ionic equation for that? Yes, you could. That would get you the 3 marks. The ionic equation there would be showing that the lithium ions, which are aqueous, combine with the iodide ions, which are also aqueous, to form that yellow precipitate. That always reminds me of the Moxil medicine I used to take when I was a kid. A sort of lovely yellow colour, the medicine that tasted bananas. And that concludes the identification question. So the final one looks at the reaction of group 1 metals. So it'd be a good idea to have your periodic table in front of you before we tackle that question. And it starts off with an observation question. What happens when sodium is dropped into water? Well, it floats, quite unusually for a metal that it floats. Okay, there's effervescence, there's bubbles, and it moves on the surface. It's a very exothermic reaction. It gets so hot that the sodium melts into a ball. Or a sphere. You get that sphere of molten metal buzzing around on the surface. You don't get a mark for saying buzzing. So those are three marks. You might also say that eventually the Na disappears. Actually, rather than just saying it disappears, might say gets smaller and eventually disappears. I apologise if you can hear some pitter-patter in the background. It started to rain and the raindrops are blowing against the window, so that's the noise in the background if you can hear that. Now, write a chemical equation for this reaction. It is so common for students to tell me that we get sodium oxide at the end of this reaction. We don't. We get sodium hydroxide at the end. So please don't make that mistake. And it dissolves. Okay, we've seen it dissolves because it disappeared. So the product must be soluble. We're not forming a precipitate. And the bubbles, well, we couldn't see what gas it is, but you could trap the gas and test it with a lit splint, which goes pop, and that gas is hydrogen. But you wouldn't report that it is hydrogen on your observations unless you tested for it. So what's on the left? Well, obviously sodium, which was a solid, and here's water, that is a liquid. Water is never aqueous, because aqueous means dissolved in water. So you wouldn't say water was dissolved in water. That just doesn't make sense. And we get to this point and we want to do some balancing. So on the right hand side of the equation, we've got 3 hydrogens, which is a bit of a pain, and we've only got 2 on this side. So I think if I try and put a 2 there, that means we've now got 4 hydrogens on the left, and if I put 2 there, that means we've got 4 hydrogens on the right. It also means we've got 2 oxygens on the right. But we've got 2 oxygens here. That works out quite nicely. We've got 2 sodiums and only 1 sodium on the left. So we fix that by putting a 2 in there. Now, how would this reaction change if we were using rubidium instead of sodium? Now, it wants us to make an observation. Now, rubidium is below sodium in group 1, and I hope you know that the reactivity of the metals in group 1 gets more reactive as you go down the group, and that's because it's easier to remove that outer electron as you go down the group, because the outer shell is further from the attractive positive nucleus as the atoms get bigger. But you wouldn't get a mark here for saying it's a more vigorous reaction. You need to say something specific about the observation. And actually, rubidium in water, you can look this up on YouTube. There's some great videos showing this, but it explodes. So be bold with your observations. Now, the question now moves on to looking at bonding. I mean, you might be thinking here, perhaps they're going to ask us a question on describe why the reactivity increases down the periodic table, and we've just talked a little bit about that. But instead of that, it moves on to talking about bonding. So it talks about the reaction of sodium with oxygen, and it forms a compound, sodium oxide. And first of all, before talking about the bonding, you need to think of what type of bonding occurs. Well, we've got a metal and a non-metal. So as we've got a metal and a non-metal, the bonding is ionic. And what happens in terms of the electrons? Well, the metal, the sodium, it loses its outer electron. It uses 1 electron from the outer shell. Okay, and that electron goes to the oxygen. So the O gains electron from sodium. Now, the sodium is happy at that point. It's lost that electron, that outer electron, okay, here has gone. Okay, so sodium has an outer shell. It is now positive. Okay, the oxygen has picked up that electron. Okay, so it is now negative. But the oxygen isn't content. The oxygen doesn't have a full outer shell. So we need another sodium to get involved. Okay, and I'm not drawing out all sodium's outer shells here, but we have a second sodium which loses an electron, donates into that outer shell. The outer shell is now full, and the charge on the oxide ion is 2-. Okay, so somewhere in this answer we need to say something about the number of sodiums. So we could insert that in here. 2 sodiums lose I was just trying to use a rubber on this this program, but it's not letting me rub out anything to do with that. So 2 sodiums lose 1 electron from each atom in their outer shell. Oxygen gains, and I'll insert 2 electrons from the sodium, and I'll put here to become 2- ion. Now you'll get 1 mark for talking about sodium losing an electron. You'll get a 2nd mark for talking about oxygen gaining an electron, and the 3rd mark comes for spotting that you need 2 sodiums each to lose an electron to give the oxygen 2 electrons in total, to complete its outer shell. They don't ask you in the question to do any of this jiggery-pokery with moving electrons around in diagrams, but just remember, if they do ask you to draw a cross and dot diagram for sodium oxide, for example, you need to show that the sodium ions, when they go, or the sodium electrons, when they go into the oxygen, are different, if you like. So here I've put the sodium electrons as crosses in the oxide ion, showing that these were the originals and these two are the ones that have been added from the sodiums. And to wrap things up, 2 questions about properties of substances. Now before you do anything, let's remind ourselves that sodium oxide is ionic. Okay, so when it is a solid, it's a giant, there'll be a giant ionic lattice. And the question asks, explain why sodium oxide has a high melting point. And the first point would be saying it's a giant ionic, or it has a giant ionic structure. Okay, giant ionic lattice. And within that lattice, you've got alternating positive and negative. It's actually 2 minus ions, but I'm just drawing this quickly. Ions. And what keeps that lattice together are the forces between the positive and the negative ions. And you need to comment on those. So the ions are attracted to each other by strong electrostatic forces. Okay, and the phrase I use when I'm teaching this, I talk about iabochi, which is electrostatic attraction between oppositely charged ions. It's not a real word though. I have had some students think it's a real word. That requires a little bit of backtracking. And these electrostatic forces are incredibly strong, so you've got many ions all attracted to each other by these strong forces. So large amounts of energy needed to overcome them. And now we might like to think about, well, what would happen if we changed the charges on these ions? And if you had a bigger charge on the ions, they're going to be attracted to each other far more. So if I had a lattice with 2 plus and 2 minus, wow, that would be an attractive force. 2 plus and 2 minus, very, very attractive. 2 minus, 2 plus, very attracted to each other. And so the forces within the lattice would be much, much stronger, so more energy would be required. And that's where this final question is going. I'm just running out of time on the video, so I'm going to write this answer up. But magnesium would have a charge of 2 plus, oxide would have a charge of 2 minus, and so it would have a very, very high melting point. And that concludes this video. So I'm just going to write that up. And thank you very much if you've been watching.